How does the potential of an electrochemical cell depend on temperature and pressure? We'll use Nernst equation. The Gibbs energy of reaction equals negative NFE. N is the number of transferred electrons in the reaction. F is the charge per mole electrons. The number is 96,485 coulomb per mole. So you can simply multiply the charge of electron 1.60218 times 10 to the power of negative 19 coulomb by Avogadro constant, and then you will get this number. And E is the cell potential, or even half cell potential. So if you want to use this equation for half cell potential, you just need to imagine this half cell is coupled with the standard hydrogen electrode. We learned this equation before. It starts from du equals TdS minus PdV, and then dH equals TdS plus VdP, and then we get dG equals negative SdT plus VdP. This is important because from this equation, we just use dG divided by dt. We get negative S if dP is 0. So over here, dG over dt is negative S if pressure is constant. Similarly, delta G over delta P is volume if temperature is constant. For a chemical reaction, we can use these two equations for the reactants, and then for the products, and then we take the difference. We'll get this first derivative of Gibbs energy of reaction with respect to temperature equals negative entropy of the reaction. So we go from here to here. And similarly, we go from here to here. And in this equation, again, we simply take the difference between the two equations of this for the reactants and also this for the products. Now we use this Nernst equation, delta G of R, the Gibbs energy of reaction equals negative NFE. We plug it in, we have delta E divided by delta T equals delta entropy of reaction over NF. And this equation holds at a given pressure. And how does this potential depend on pressure? Over here, similarly, we have negative delta V of R divided by NF. On the right hand side, these two are just more general case. I put a knot here to specify the standard state. When you put a knot here for a cell potential or for a reaction, it means every single chemical is in its standard state. This is a hypothetical situation. The temperature dependence of the cell potential. So how does the cell potential depend on temperature? We can use this to determine the standard entropy of the reaction. And also, if we know how this standard cell potential depends on pressure, we'll be able to get the change of the volume in the reaction. Usually this is negligible because most electrochemical cells include only liquid and solid chemicals. But in case you find the dependence of this cell potential on pressure is significant, that suggests gas species are involved in a chemical reaction, and also the number of moles of gases changes in the reaction. So again, this is the Nernst equation, and for a more specific In a hypothetical situation, if every single chemical involved in the reaction is in the standard state, we have a corresponding equation here with just one additional knot in the superscript. And we learned this equation before. Delta G of R equals delta G of R in the standard state plus RT ln Q. This Q actually takes the difference between the actual state of the chemicals and the standard state of the chemicals. And then similarly, we have the cell potential equals the standard cell potential. And over here, it's minus RT over NF ln Q because of this negative NF here. At a chemical equilibrium, the Gibbs energy of reaction is 0, and the cell potential is 0. The reaction quotient at equilibrium is called equilibrium constant K. And then we have this equation to relate the equilibrium constant and the standard Gibbs energy of reaction. Similarly, K can be expressed as a function of E naught, the standard cell potential. And vice versa. The standard potential is simply RT over NF times L and K. Over here, those are the equations that relate the equilibrium constant to the standard Gibbs energy of reaction or standard cell potential.